Welcome back to my lecture, Mechanical Behavior of Materials, course number 315008. I'm Klaus-Dieter and we are writing the spring semester 2022. Last time I started with the theory for dislocations. So to introduce dislocations, first of all I talked through the theoretical yield strengths of materials. If we look to a tensile testing, then we can realize, as we take a single crystal as a test object, that there's deformation, plastic deformation on so-called slip planes. And these slip planes, they're important, they're crystallographic planes where the atoms, they change from one potential minimum to the next potential minimum, like demonstrated here in that sketch. We cut the crystal along a lattice plane and then we displace it along the lattice plane under some applied stress. And when we relieve the stress, then we have the new set of lattice planes, and there's no reason why the crystal should go back like in a elastic experiment, because locally the crystal looks like a perfect crystal. We only get a step at the surface, and that is the plastic deformation. We talked about the theoretical yield strengths, which we get by the assumption that we displace all the ripples, all the atoms at once. So we displace the top layer with respect to the bottom layer in one step, where each layer is stiff. That means we need to lift up the top layer out of the potential minimum here to the top and then lock into the next potential minimum here. By estimating and approximations, we got theoretical strengths for the shear stress, which is G over 2 pi, and G is the shear modulus. We know G is in the gigapascal range or many gigapascal range, and that gives us this table. So if we compare the table, here we have the G over 2 pi in gigapascals for silver, aluminium, copper, nickel, and so on, a lot of metals, and we get the experimental yield strengths and find that there is a discrepancy of many orders of magnitude, up to 4 orders of magnitude. Sometimes it's 2 orders of magnitude, 3 orders of magnitude, but most of the time it's 4 orders of magnitude. So there's a problem. Then people look to the theoretical yield strengths of a dislocation-free whisker. So this is a crystal without any dislocation. A whisker is a very tiny, long crystal, like a string, but it has a certain zone axis, and it is crystallographically perfect. Sometimes it has one dislocation, but this is a dislocation-free crystal. And they are about the strongest materials you can find. We see that because the theoretical yield strength, this G over 2 pi is still the same as before, but then the experimental strength is already higher than in the polycrystalline material here in the table to the left. So the whisker has higher experimental strengths than the polycrystalline material. This is something we want to note down already for later. But still there is a factor about 6 or about 10 in average weaker than the theoretical yield strengths we have estimated. So still there's the question, what is happening? Why we are not reaching the theoretical yield strengths? Or why is our model this onset with displacing the ripples like a fixed cardboard? Why doesn't it match? So take one of these cardboard layers and put the other one upside down on top of each other, and then try to shear it. You need a pretty high strength to lift it up and displace it. Yes? Any question? Not yet? Good. So this gives us now the introduction to another theory of plastic deformation, which is the dislocation theory. So first of all, I like to introduce dislocations. Dislocations are line effects. We talked about that in contrast to point defects and electronic defects. Or point defects are 10 to minus 10 meters, 1 angstroms. We know that. A vacancy, you mentioned that last time. And volume defects are bubbles and inclusions. Then we have the line defects, they're in between. And also interfacial defects, which are grain boundaries, for example. Then Vito Volterra, he looked into these types of dislocations macroscopically, but we look to it microscopically, where dislocation, and this is, I guess, the last slide I've shown last time, or one of the last slides. So this is where I want to continue today. Remember, we have a perfect crystal, as shown here, and then we introduce half a plane from the top, which ends up here. It's like inserting a sheet into a book. So you can say these are the pages of a book, and you put one sheet in between which does not go to the other end of the book, which stops somewhere in the middle. And that is a line that describes a line, namely where it ends, or here it ends like this, and at the surface, of course. And this line is called a dislocation line. So because this is like an edge, we call this an edge dislocation. We come to other dislocation, the screw dislocation later on, and also mixed dislocations. I talked about the Burgers vector. We will talk more about the Burgers vector. Here just shown in the 3D rendering the dislocation. So we have the one extra plane which is inserted half into the crystal until this line, the dislocation line, which is shown here. We look along the dislocation line in this case and see the upper atoms. Of course, here far away we have the lattice parameter, the translation invariant vector between the lattices, atoms and lattice planes, and the same here at the bottom. But of course, in the vicinity of the dislocations, the distances between the atoms and the distances between the planes, they have to be strained a bit. You see, there's some longer and there's some shorter, just to match it out. So you have to elastically deform the crystal lattice around the dislocation. And this is a strain field around the dislocation line, which will be important later on in this course. So how does a dislocation move then? For example, we have a dislocation there in the first figure and apply shear stress as shown there. So here we push in this direction, and at the top we push on to the right. We have the slip plane, which is this plane, just above or below the dislocation. It's below the dislocation. So the dislocation ends on the slip plane. This is where the dislocation line is located. You see the plane above has more atoms than the plane below. One row more of atoms in the plane above. So this is called the slip plane, and we have the dislocation. Now we have this bond here, which I point out, and if we connect now on the right hand side this bond and this bond, then eventually this intermediate step is shown there. The bond is connected to the left. Here this one is still connected to the right, and in the next step we can move this to the left, and so on. Means that this dislocation moves through the crystal on this slip plane until we reach the surface, and at the surface we get an atomic size step, the unit step of slip. And this is also the Burgers vector in this case. In other words, there's this analogism where we have a caterpillar. The caterpillar lifts up the back, the tail, and pushes it a little bit forward. So when it was straight, the tail was here, then it was pushed forward by this Burgers vector. And then this buckling goes through, and the buckling advances to the head, and eventually you come up with a strain-free caterpillar again, so a flat, long, one-dimensional caterpillar, which has been displaced by Burgers vector, by the amount it lifted up the tail at the very beginning. And again, this is demonstrated in the crystal that is to the bottom, but I think I have this movie here. There it is, made by Todd Hufnagel. So now I show to the top and at the bottom, these white arrows are the application of shear stress. And let's start now. Shear stress goes to the right and the dislocation moves to the right. Then we have the step at the surface, we inverse the shear stress and the dislocation moves back. Then we do it again, shear stress to the right, at the top we get the step, dislocation, shear stress to the left, it moves back, so it removes the step in the ideal case, or it slips on a different plane. So I hope here you can see how the dislocations move. Right. Dislocations we find at many occasions in nature. For example, the stripes of the zebra shown to the left top. There are continuous stripes as here on the fur of the zebra. But sometimes you have one stripe inserted. And here's another stripe inserted. And that's called a dislocation. So this is dislocation point. If it would be three-dimensional, it would be a dislocation line. Or we see here in the corn. In the corn we have these continuous lines of seeds. And these seeds, sometimes you have a point effect, as shown here. You get one more seed included. Or you may also get a line included. So here, for example, at the top we see that there are lines included. Here also something is happening. Yeah, here we have a straight, here we have a straight there, and here we have half a line included. I'll remove the color so that you can see it again. Caterpillar, I talked about it. It's shown here in the cartoon to the right, how the caterpillar moves. So remember that this is the way how dislocations move. Also, I like to be outdoors, so these are ripples in the sand, a picture I took, and we see there are these ripples, and there are continuous ripples, and there's ripples there like this, but eventually we get one half ripple inserted there. And you see that at other locations. Yeah, here's a ripple, and here's a half a ripple inserted. So dislocations occur everywhere in nature. Yeah, it's a dislocation. So it's where the dislocation is interrupted. Location, yeah, and the dislocation, or the location is displaced. We also call them discontinuities and so on. So I've talked about the edge dislocation. Again, here a little slower in this schematic movie. We apply the stress now as shown, and you see the dislocation jumps from one lattice position to the next lattice position until it reaches the other surface. And then of course you can further deform the material by pushing a second dislocation through, a third and fourth dislocation. Many dislocations you can push through to get high plastic strain. How do we find the dislocation? Well, we go up in a lattice, or we start at a point in the lattice, and then we go 1, 2, 3, n steps in one direction and m steps in the other direction, and then we get the n steps back. So n is 3 here in the horizontal, and 1, 2, 3, 4, 5 up, 1, 2, 3, 4, 5 up. Then I should end up at the same position. This is in a perfect lattice where we have translation invariance. Now if we go around the dislocation as shown here in this figure, then we go 1, 2, 3, 4, 5 steps to the right. We go 1, 2, 3, 4, 5 steps to the bottom. Then we go 1, 2, 3, 4, and I would go 5 to the left, and I have to go 5 up again. So 1, 2, 3, 4, 5, and I would end up here. So I would end up at a position which is shifted to the left, which we call the Burgers vector B here, shown in green. If I go a loop and I end up with a Burgers vector, then I have this shift. Or if I go a closed loop around the dislocation and I do that somewhere in the perfect crystal, then of course I have also a relative shift. The one is relative to the other. So I do it the way as I've shown here. I go m steps in this direction, n steps down, minus m steps to the left, and n steps up. And if there's a dislocation, then you end up with a different position. If there's no dislocation, just bent lattices, that can be bent lattice planes, then you end up at the same position. Sometimes it's difficult to see the point of the dislocation, because we will see later on this dislocation has a width, can spread over many lattice planes. So, what is the Burgers vector? Just to the vocabulary. Burgers vector, is it this? I know you're getting hungry, but first we have to get through the course, and certainly it's not this. It's not this Burgers. It's this Burgers. So this is Johannes Martinus Burgers, or Jan Burgers. You spell it like this, B-U-R-G-E-R-S. In contrast to this burger. Yeah, if you have a burger from the fast food, it's a burger, and then apostrophe S vector. This is not the case. It's the case of this guy. So be aware how you spell it. The Burgers is part of the word. It's not part of the the apostrophe. So Burgers also, there's more confusion even with Burgers, because they're two brothers. And both brothers, they are physicists, or have been physicists, at the TU Delft in the Netherlands, Technical University of Delft, famous university in Europe. There was Johannes Jan Martinus Burgers, who lived in 1895 to 1981. But also there was William Gerald Burgers from 1897 to 1988. And they're both important for material science because now we know the Burgers vector. I just introduced it. And probably many of you know the Burgers orientation correlation, which is between the HCP and the BCC lattice when they perform a phase transformation, a displacive phase transformation. Then you get the Burgers orientation correlation. This is not part of the course, but we can talk more about it if you're interested offline the course. So be aware, the Burgers vector is attributed to a different person than the Burgers orientation correlations. Now we talk about Jan Martinus Burgers, or Johannes Martinus Burgers, to the left. I like to come to the other type of dislocation, namely the screw dislocation. In the screw dislocation, you take the perfect lattice and you cut it just halfway, like cutting in a piece of cheese or tofu, and then you skew it. You shear that part to each other here in the vertical direction. This is also shown here to the left in that blue animation, where we have the propagation of a screw dislocation while applying shear stress. So this basically, the blue item is rotated 90 degrees to the right hand sketches. On the right hand side we see also how they draw this counting, the number of lattice positions around the dislocation line, and find a Burgers vector which is vertical on the right hand side. So that's a screw dislocation. Here more about the screw dislocation. So first of all, we cut it here, then we displace it, and this is now a little like Vito Volterra's other studies, where they have the pipe and they cut it and then they displace it along the axis. So this is the axis of the cylinder, and the Burgers vector, the displacement here, is also axial, along the axis, along the line. So this is now, when we go plane by plane, we see we go once around the dislocation line and we end one layer up. This is like going in a car story building, as shown here, where we have these screws to drive up or down. So let's characterize the dislocations a bit further. I introduced the edge dislocation and the screw dislocation. In the edge dislocation, for the movement, well, first of all, we have a dislocation line, which is this direction. And as we apply a shear stress, it will move, and the direction of motion is given here. So it's parallel to the Burgers vector. The slip direction in the edge is parallel to the Burgers vector. But it is perpendicular to the dislocation line. So dislocation line is this direction, while the slip direction is that direction, Burgers vector. In the screw dislocation, it works like a zipper. You open and close a zipper. You know that for the jacket or whatever, for your bag, handbag has a zipper. We apply the shear stress like this and like that. And the Burgers vector is along this shear direction. The dislocation line is now parallel to the Burgers vector, and the direction of motion is perpendicular to the Burgers vector. I can demonstrate that in a sec. So the angle between the dislocation line and the Burgers vector is parallel in the screw, and the line of movement with respect to the Burgers vector for edge is parallel, for screw it's perpendicular. I have to check what I have here on the table. A lot of crap. So what is this? So this is a piece of paper. You see the piece of paper? I apply a shear stress, and there is this propagation. I pull in the horizontal direction, yeah, but you see there the propagation is down. The propagation of this opening goes down, and that's a little like the screw dislocation. I pull here left and right, the shear, but the direction of motion is perpendicular to it. A bit like a zipper. Also in the edge, B cos u is the slip plane, which we call n, the normal vector to the slip plane, reciprocal lattice vector. And in the screw dislocation case, B cos u equals 0 and B dot n equals 0. So B is perpendicular to the slip plane as well. Then we have the question, how can the dislocation leave the slip plane? So here we are on the slip plane. How can the dislocation go on another slip plane which is maybe up? And this we call, in the case of the edge dislocation, climb. So the dislocation has to go up from here to there. We climb up the slip plane, and in the case for screw dislocations, this is cross slip. And what cross slip is, I introduce this in a sec. The climb is non-conservative in work. We even have to add atoms or remove atoms in the climb, while the cross slip is conservative in work, so mechanical work. So I stay with this slide because I want you to digest this slide. This slide is very important, which you should know by heart or have it on your formula sheet. Particularly these correlations between slip direction, slip dislocation line, the normal, the slip plane normal, line movement, and how to leave the slip plane by climb or cross slip. So this slide resumes everything, but we talk through it more in detail. I promised you to talk about cross slip. So cross slip is when the screw dislocation propagates from one plane to another plane. Here we have a screw dislocation. And remember, screw dislocation moves perpendicular to the Burgers vector. We had that here, yeah? Slip direction, moves parallel. Sorry. Moves perpendicular to the dislocation line. There's something wrong. I'm not sure. But the Burgers vector is here. U is parallel. U is parallel to B, and we have the movement of the dislocation line goes perpendicular to the Burgers vector. So that is shown here. We have the Burgers vector and we have the movement of the dislocation line which propagates from the back here towards this edge, so towards this line. And as it reaches this line, it may be energetically more favorable that it goes down on another plane. Crystallographically, this is a slip plane here, which is the 111 plane, and this is another slip plane, which is the 1-1 plane. Particularly in a cubic system, so FCC lattice, we're talking FCC lattices where the slip occurs on 1-1 planes. Then the 1-1 and the 1-1 are the same type of planes. They're only different by the orientation, but the local symmetry, the local environment is exactly the same. This is crystal symmetry. So, as we see here, we are on one 1-1 plane, moving onto another 1-1 type plane, and then propagating there. And eventually, this can happen again, going back to another plane, which is of type 1-1, or which is parallel to the original 1-1. And this we call cross slip. So then we have transferred the dislocation line from this 1-1 plane to that 1-1 plane, which in this sketch is further down. Right, so again, here's the figure 3.9 from this textbook on dislocations. The sequence of events A, B, C in cross slip in the face-centered cubic material. The -1, 0, 1 direction is common to the 1-1 and the 1-1, 1 close-packed planes. So this line here is common to both planes. And then a screw dislocation at S is free, so at the line here, is free to glide in either of these planes. And it glides into which direction? Where we have the larger resolved shear stress. Yeah? So if the larger shear stress tau is in this direction, then it would continue like this. If the larger shear stress at this location goes on the other plane, then it goes on this inclined plane. So it's the resolved shear stress. And what the resolved shear stress is, we come to that also later today. And the cross slip produces a non-planar slip surface. So you see the slip surface is non-planar. And there's double cross slip shown in the figure D here. Now I've talked about screw dislocation and edge dislocation. And we can have mixed dislocations which have both characters, as shown by this blue circle or blue arc between the pure edge and the pure screw dislocation. We see here on that face of the sample, we have all character of the edge dislocation. The dislocation line here is normal, or lies in the slip plane. The Burgers vector is this direction, so dislocation line is perpendicular to the Burgers vector, and we have here this inserted plane. While if we rotate 90 degrees, we go to the pure screw dislocation. Yeah, it's like cutting the crystal along this plane and then shifting it by this yellow shaded Burgers vector. So that's all the character of the pure screw dislocation. Burgers vector is the same. It's always in one system. There's only one Burgers vector. And we see the Burgers vector is parallel to the dislocation line in this point. In between here, we have mixed dislocations, though they have some screw character and some edge character. This leads to the concept of dislocation loops. So let's assume we have a Burgers vector here, and we have that plane which we cut along this ellipse and then just displace this pink part by the Burgers vector B. So we have dislocation lines. The dislocation line goes in this loop where we have parts with the Burgers vector parallel to the dislocation line, so screw character, or anti-parallel, it's also screw character. The one we say it's a left-handed and this is a right-handed screw dislocation. And here we can say we have edge dislocations, so Burgers vector and dislocation line, they're perpendicular to each other. The same on the left-hand side. Burgers vector and dislocation line, they're perpendicular to each other. And on the left-hand side, it's like introducing a plane from the top. And here it's like introducing a plane from the bottom to this pink plane. So this is a dislocation loop inside the crystal lattice. Here we have the motion of the mixed dislocation. So if we apply a shear stress, you see here we have a Burgers vector and we apply a shear stress along the Burgers vector, then we get at the edge dislocation we get the motion in the direction of the Burgers vector. At the screw dislocation we get the motion of the dislocation line perpendicular to the Burgers vector, and since the sign changes at the bottom, it moves here, and at the left it moves there. From left-handed or right-handed screws, or introduce a dislocation line at the top, or a dislocation plane at the top, or from the bottom, it moves in the opposite direction. So as we slip the top figure, we see that the dislocation loop increases. So when we shear along the Burgers vector, the dislocation loop in diameter increases generally. And if we slip in the opposite direction against the Burgers vector, then it would shrink, it would decrease. We see that also, that slip process here in the cartoon movie to the left. So we will start, now we start with dislocation and we move them down, and you see they move down, and you see where the blue atoms go and where the red atoms of the layer above go. So it's marked here. We are looking at the plane of the cut, sort of a semicircle centered in the lower left corner. The blue circles denote atoms just below, and the red circles just above the cut. Up on the right, the dislocation is a pure edge dislocation here, and here at the bottom it's a screw dislocation. In between is it mixed. So, I've shown the animated illustration already here in the slide. There's, I think here's a link where you can see it as well. So again, this is the expansion of a dislocation loop. I have a Burgers vector here, B, and I put a shear stress along B. So here from the bottom along B. Then I get an increase of the dislocation loop, and when the dislocation loop hits the border of the crystal, then the, let's say the cube, the regular shape, ends up with a step. Ends up with a step in the orientation of the edge dislocation.
Yes.
I would say we have a break now. 10 minutes break. I want to stop the share here. Yeah, let's have a 10 minutes break, and then I continue with these dislocation loops and more on dislocations. I see there's a chat. Okay. See you now in, yeah, let's say at 5 o'clock at your place. Good. Okay. Bye. Oh, see you shortly. All right, let's continue. I hope you can hear me.
Yes.
Yeah.
Professor, I want to ask a question.
Yes, please.
I still don't understand the term you said in the edge dislocation. Like, why the dislocation leads in the climb direction?
Dislocation climb.
Yeah.
Yes, good question. Let me see. Okay, dislocation climb. Dislocation climb, and we come to that later, is we have here lattice planes. And then we put a dislocation in here. So we put one extra vertical lattice plane in there. At this location, at least this position here. And now we want to, or this can move on this slip plane, right? So I can move left and right on this plane. So I can go from here to there, to there, to there, and so on. Now the question is, how do I get it on another slip plane? So let's say it is here, and I want to get it one plane up. Then I have to remove one atom here. and actually because this is a whole line, I have to remove a whole line of atoms perpendicular to the drawing plane in the third dimension. And that's called climb. And for that we need diffusion. So at room temperature it would not work, because we don't know where to put these atoms. It cannot climb. But at high temperatures we will see it will climb by diffusion, by putting atoms there or by removing atoms through vacancy diffusion mechanisms. Is this approximately your question?
Yeah.
So for edge dislocations we need the climb to change the habit plane of the slip, while for screw dislocations we can have this cross slip. And a cross slip is just we move from one slip plane to an inclined slip plane of the same crystallographic symmetry, or maybe even a different one. But we can go to another slip plane, and that's a fundamental difference between the two types of dislocations. For the one we need diffusion, add and remove material, that's why it costs work, it costs energy, yeah. While for slip it is non work consuming. I hope I come to these aspects later during this course. For sure we have the one or other example, because also plays, as diffusion plays a role, this is high temperature, and that will play a role in the creep, when we have dislocation creep. Not in this lesson, that comes, there's a lesson on creep later on. But even before we talk about climb. Okay, so if this roughly answers your question, I will continue. I have mentioned the expansion of the dislocation loop due to the different characters of edge and screw, and also the sign of the edge. Once you introduce a plane from the bottom, once you introduce one from the top. Let's say here you introduce one from the top, here you introduce one from the bottom. And then these dislocation loops, they can increase to a macroscopic displacement like this. I mean a final body displacement like that, plastic deformation. I want to talk about some types of dislocation loops. So you also should be aware of different dislocation loops. There's a glissile loop. Glissile means to glide. Glissile, glide, gliss, yeah, gliding. So a glissile loop is what I just have shown before, in contrast to the sessile loop. Sessile comes from to sit, or a seat. So it's sitting there, it's sessile. Please remember this vocabulary, because that's quite common in literature. And then we also have another vocabulary, which is the prismatic loop. Prismatic because the loop is along the faces of a prism. We see in the first case we had this planar configuration where the Burgers vector is within the slip plane, or in the plane we consider. In the loop plane, yeah, not the slip plane, it's within the loop plane here. While we can have the Burgers vector perpendicular to that loop plane, or with the angle inclined to that loop plane, and that we call a prismatic loop, because a prism is something like shown here from Wikipedia. You get these different shapes of prisms. basically a body with a base and a cover, which are the same, and then the sides you just connect by faces, and these faces, they are parallel to each other. That's a prism. I mean, they have a common zone axis. There's an axis, and the face normals, they all have these face normals. They're all normal to the zone axis, which in this case is vertical. Right. So a glissile loop, again, here in the figure to the left. Repeat this several times in different figures because it's important for you, for me, that you understand it. So we have the Burgers vector here. That means here at this position at the top we introduce one lattice plane. Means also on the other side we would have, if this is the outer radius, we would have a negative Burgers vector, or introducing a lattice plane from the bottom. Yeah, it depends how you see it. A negative Burgers vector, or introducing a lattice plane half from the bottom. And then on one hand we have a left-handed, and on the other side we have a right-handed screw dislocations, which may be shown by those symbols. So a screw is something which goes around the cylinder, and then we put this bar to the bottom or to the top. So it's something like a omega and bottom omega on the other side. The prismatic loop is schematically shown to the right. So we have the plane of the loop again, and the Burgers vector is now either perpendicular or with some angle, some crystallographic angle towards this line, towards this plane of the loop. And we see there are edge dislocations all around. So inside is one plane missing, because outside everywhere you have one lattice plane inserted in addition to the inside, or you can say inside there's one plane missing. Can it move or not? Is it sessile or glissile? It would not move if you put a shear stress like this along the plane. Of course, then it cannot move, because the movement of the dislocation is up and down, yeah. But of course, if you push here with a pencil from the top into the cylinder, or from the bottom, with respect to the cylinder, so you put a shear stress here and there, they're up, and inside you push down, then it can move up and down along the cylinder, or along the prism. Remember, it's a prism because it can be a cylinder if it's continuum mechanics, and if you do the crystallographic phases, then it's more like a prism. But we call this a prismatic loop. So here are some prismatic dislocation loops. As I said, in the center you can have one lattice plane missing. So here's one lattice plane missing. But on the other hand, you can turn it around. You see here the dislocation is shown like this. The extra plane is to the outside. But you also can put an extra plane to the inside. So you put just a piece of paper into your book. A round piece of paper, a small facet note sticker inside your book, which is fully surrounded by the book, or in this case with lattice planes. The first one we call intrinsic, and the other one we call extrinsic dislocation loop. Intrinsic is you remove something, so it goes inside. The other planes, they go inside the hole here. And extrinsic, you put some extra stuff in. As shown here, we put this piece of extra material in, which in 2 dimensions is this loop, the border. These loops have been observed here experimentally. So when they heat aluminium to 375 Kelvin, tattoo or wash burn, they have seen these loops eventually moving and changing shape. You see here, after 0 minutes, they have this hexagonal shape, and if you wait a long time, 213 minutes, they become more round. And this is because at higher temperatures you also have more diffusion, so you're less sensitive to lattice orientations, and eventually they may move and change. Here you see, just interpret this, because we have diffusion and this is climb again. So if here we have an intrinsic loop, you can condensate extra atoms there, so the loop becomes smaller and smaller. And this is annealing. This is annealing of material. You know, when you anneal material, it becomes, most of the time, becomes more like a perfect crystal. You remove not dislocations, you remove generally defects by annealing a crystal. Right, here also dislocation loops in silicon. This was my very first paper in my master's thesis, so to say. In situ neutron diffraction study of lattice deformation during oxygen precipitation in silicon. I started with in situ studies, and we published this figure here, where we, in diffractograms, we can see the evolution of lattice strain due to the expulsion of dislocation loops in silicon. And there are figures here by other people, as shown here to the references. For example, Strunk and Kolbesen. They show this figure here, the thermal decomposition. So what happens, oxygen precipitation in silicon, silicon has supersaturated oxygen in the crystal lattice. And when we heat it up again, this is from the production. So the production of silicon, it's above 1400 centigrade. I forgot the melting temperature, but at very high temperature, and then it's cooled down relatively fast, and you get oxygen dissolved, which comes from the crucible, inside the silicon. And then it's quenched to room temperature. So it takes a long time for the precipitation. It is quenched to room temperature, and you get supersaturated solution of oxygen. When you heat it up again to some lower temperature, like 1458 Kelvin here for 36 hours, then we get very broad reflection curves. At the beginning we had a very sharp reflection curves. So this is an upside down reflection curve. And this is because we get precipitations of silicon oxide, and the silicon oxide takes more volume than the silicon which was at this position before. And therefore, it induces stress on the surrounding matrix. So on the matrix, we get stresses, including shear stresses. And these shear stresses, they plastically, or they relax by pushing dislocations into the system. So the stresses are above the yield limit and push dislocation loops into the systems. Now these dislocation loops, they are sent out by these precipitates, and they make large range strain fields, and that can be used for gathering impurity atoms, heavy metals, in silicon. When you have, for example, a surface or a silicon wafer shown here in vacuum, then you have oxygen, and the oxygen, you all had the diffusion course, so you get a depletion of oxygen near the surface. And here near the surface is this depletion of oxygen through degassing into the vacuum. You have done that in the diffusion course. And then at longer time scales you get precipitations of where you have oxygen. So you see there are sharp layers where we have precipitates of silicon oxide here, and layers which are depleted of oxygen without precipitates. And that's good, because electronics we build onto the surface. The electronics we build on top of this depleted layer, pure silicon layer. Then we have a lot of strain fields due to the dislocation loops from these precipitates in the bulk. And also, if you remember diffusion, the impurity atoms others than oxygen, like metals, iron, copper, and whatever you have in there, they can move along, diffuse along the gradient of the strain field and get gathered here. So they get bound in the strain field. Means at the surface we get also depletion of other impurity atoms. So this is industrial applications of using dislocation loops in perfect crystal silicon to make the surface even more perfect in terms of solid solution atoms. All right. Now let's, from this background information, I like to come more into some formal considerations of dislocations. So we say dislocation, or in general we say we have a disregistry. That means the displacement. We register the atoms in the original crystal lattice. So here, these open circles, you see, they form a perfect crystal lattice. It's all regular translation invariant. If you go one step of the open circle to the next open circle, it's always the same displacement vector in the horizontal, and another, in this case cubic, quadratic lattice in the vertical, or you can go diagonal. So it's a perfect crystal lattice. That's how we introduce a perfect crystal. And then we put a dislocation in. So one extra plane we put in here at this position along the y-axis. So we call this the y-axis. We put y equals 0 here, and the other axis is the x-axis. Now we can look, if we go far away, the white atoms, they should have the regular lattice as before the open circles, the black atoms, yeah? So if you go far away from the dislocation, the strain field, displacement field, or strain field should be relaxed. So we have the same distance. But obviously, close to the dislocation, here in this case we have a larger distance. And there, from there to there, we have a slightly shorter distance, because here we have to put two of the shorter distances close to the one larger distance. And only if we go far away from the dislocation, then the lattice becomes straight again. Yeah, if we go far away, then we have the straight lines again if we go along the y direction. So we call, now the question is how far can be this displacement u of a. You see the original atom was here. Now we put the extra plane in at x equals 0. That means this atom which was there displaces by u of a. So u is the displacement as we had it before along the x direction. So it's u in the plane A, and we have a u in the plane B as well, which we call u of B. Or if you call the plane A, B, C, D, A1, A2, A3, then it's u of position Y. But we look to the two planes A and B, and they are separated here by the lattice parameter A, small a. So remove the ink. So you see the big A is the one plane and the big B is the plane below, the slip plane. They are separated by the lattice parameter A along Y. And we measure the displacement u of A and u of B. Now, how far can u of A be? It can be half, yeah? If it's half, if the displacement is half, then we cannot say it belongs to the left or to the right hand side. If it's larger than half, we can say it's the other. We always have in crystallography the plus minus translation vector t. So we always can add 1 or subtract 1 times the periodicity, which is b in the horizontal direction along x, b because that will be the Burgers vector. So we always can add or subtract 1 lattice translation vector b. And that means we can, the u can be from 0 to plus 1/2 if we displace to the right, or from minus 1/2 to 0 if we displace to the left. So it can be between minus 0.5 and plus 0.5 as shown here. So this is u over b. Or delta u over b. Now we talk about the dis registry. The dis registry is smaller than half the maximum. Half the maximum is 0.5 b. So half the maximum is 0.25 or 1/4 of b, and minus 1/4 of b. So if the delta u is between minus b quarter to plus b quarter, we call this the dis registry delta u. And now the question is, how does the delta u change as a function of x? So this is the function x. And how does delta u change from 0 to to 1 or minus b fourth to plus b fourth? It can go in a broad way, or it can be in a narrow way. So in the broad way, even far away, you see here many lattice planes away from the dislocation at x equals 0, we still have measurable disregistries, so displacements. While in a narrow, it relaxes much faster in a narrower band. And this we call the width of a dislocation. So W, it's the width of the dislocation where the disregistry is within this interval minus b fourth to plus b fourth. Of course, the delta u can be minus b half to plus b half, as shown there. And half of that, it's minus b fourth to plus b fourth. So it's something like the full width half maximum. If we take the derivative of that curve, then we get this peak here, and the derivative of the narrow curve gives you a narrow peak, while the area of the displacement must be b, must be the Burgers vector b. So this is when you integrate over all disregistries, the total disregistry is the dislocation, which is the Burgers vector b. So this is not a strain, this is a stress we are introducing here. And from the strain we can go to the stresses by using the shear modulus. And now we say we have this behavior for perfect lattice that tau c is approximately g times e to the minus 2 pi w over b. W is given by a over 1 minus nu. So nu, we have also the Poisson's ratio. In the perfect lattice, the tau is g over 2 pi, and we put everything together, then tau c is approximately g times exponential of minus 2 pi a over 1 minus nu times b. So b is the interatomic spacing. This is our Burgers vector. This is how much we slip. A is the interplanar spacing, so in the y direction, perpendicular. And W is the dislocation width. So here we put the width into this formula. Right, I'm just looking here to the figures. We have the slip vector, we get a shear stress applied, and if we look as a function of x, we get this Peierls-Nabau energy barrier, which for a wide dislocation, to move b force, I have to go a far distance away, and a narrow dislocation, I have only to go a small width away from the insertion of the extra plane. So what I want to express here is that the critical shear stress goes with exponential minus the width of the dislocation. And the wider the width of the dislocation, the smaller the shear stress. This is the essential you have to take with you. Here's a table of the effect of the width on the shear stress derived by Piles and Nabarro in the 1940s. If the width is 0, then the shear stress will be G. If the width is approximately B, then it will be G over 400. That's the order of magnitude. Here's the formula. If we put it in, so e to the minus 2 pi b over b gives G over 400. If it's 5b, then the shear stress is G over 10 to the 14. Oh, that's small. And if it's 10b, then it's G over 10 to the 27. That's extreme small numbers. Looking to various materials, namely metals with FCC lattice, so silver, copper, brass, alloys, nickel, aluminium, then the strain width is wide, the dislocation width is wide, and that means the Pile-Nabarro stress is low. And also temperature sensitivity, this is not directly coming from out of this formula, but it's in the table, it's very small. The Pile-Nabarro stress is low for metals. If we go to metals with the BCC structure, iron, tungsten, moly, niob, the strain is narrow and the Pile-Nabarro stress you need to deform these metals is medium. And we know that already from daily practice, that the FCC metals, your gold bracelet, silver, if you make it pure, copper, annealed copper, they're very soft materials and very ductile because the Pile-Nabarro stress is low. Metals like BCC iron or these other metals listed here, they are pretty hard. They're much harder than the FCC, and this is because the strain width is narrow, and thus the Pile-Nabarro stress becomes medium. And they also have a strong temperature sensitivity because of activation processes. Ceramics, they have ionic binding. Then the strain width is narrow because these ionic bindings, they are pretty strong forces, and thus the Pile-Nabarro stress is high, and it also has a strong temperature sensitivity due to activation processes. And now we come to ceramics which have a covalent binding. The covalent is kind of the strongest bond we have in the crystals. So the strain width is very narrow, and therefore the Pile-Nabarro stress is very high. And we know they are very hard materials. We can compare that to the hardness because the hardness is withstanding the plastic deformation. Also, it shows strong temperature sensitivity. So what I want you to take away is that we can have a width, let's say full width half maximum, or the half width of this registry. So from here to here, the displacement with respect to straight lattice planes plays a role, and goes exponential into the shear stress, into the critical shear stress tau c. Next chapter. How much time we have? 11:37. So 17:37 in your place. Let's now talk about the observation of dislocations. Very simple observation of dislocations, and that's what I did as a student as well. You take the crystal. I took a gallium arsenide crystal. I worked on gallium arsenide. I needed to know the dislocation density. You throw the single crystal into an acid and etch. So you remove atoms from the surface, and you know already the potential at the surface depends very much on this local strain field, local stress field, local strain field. And it turns out that at dislocations you get enhanced etching. And you also know along certain lattice planes you also get enhanced etching with respect to other lattice planes. And that's why you get these dislocation grooves. Etching grooves around the dislocation, or etching pits. The pit, the groove is one-dimensional, pit is zero-dimensional. It's just a point. And we see that already, expansion of a single loop of dislocations in lithium fluoride. Okay. So I didn't look up the literature behind this figure. Just want to show qualitatively. But apparently there is a dislocation loop somewhere which hits the surface, which you cut at the surface. So a loop can end at the surface. A dislocation can either loop around or it hits the surface or interface of something else, yeah, dislocation, grain boundary or precipitate. But it cannot end like this in the volume. Doesn't go from the topological point of view. So what is shown here, also critical shear stress necessary to move a dislocation. Yeah, I haven't looked up that paper. But we look to the observation of dislocations. Of course, we can do electron microscopy. Electron microscopy is a perfect means to look to dislocations. See here the scale bar is 0.2 micrometer, that length. And we see various loops. Loops which are zigzag, loops which are more oval shaped and or hysteresis shaped. And the shape of the loop depends very much on the crystal orientation and depends very much on the process which you have introduced the dislocation. Here also we see forests of dislocations, or many dislocations, and then we see areas where there's no dislocation. So these are all special cases just to show that they exist. Dislocation in metals. Here are some of titanium, inside titanium, and in silicon. I talked already, dislocation loops in silicon. Silicon, they have covalent bonds, so dislocation widths are small, and that also means they follow preferred lattice orientations with edges, yeah. So we can see they have relatively sharp corners because the bending that may widen and the dislocation widths in the bend, which is not favorable for the covalent bond. So we get more the lattice oriented directions, while in titanium And metals, soft metals, they can be more zigzag, so more arbitrary orientations. And this is also when you have a wider dislocation width, then it can jump from one to the neighbor location. Here others in aluminium oxide and titanium carbide. Examples. We have already mentioned the elliptic dislocation loop when you apply a shear stress here over that plane of the loop. Then you have here this lattice planes inserted from the top. Here you have planes inserted from the bottom. Here you have a left-handed and here you have a right-handed loop screw dislocation. We can have arrays of dislocations. So we will see later in this lecture, not today but next time or so, that the dislocations, they can line up. They can line up in regular orders like this, on top of each other or next to each other in a very regular way, and can form this dislocation arrays. It's kind of a super lattice with within the crystal lattice. So the crystal lattice is very fine here in between, and after n distances we find the dislocations. So here they are up, down, up, down, up, down, or they can be all up, 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 up. So there are various configurations, and we will see later in what under which conditions they form which kind of arrangement. There is pile-up of dislocations, also very important. We come to for plastic deformation in polycrystalline material. So what we see here, this may be edges, etching pits, and we see a lot of dislocations lining up along this line. And here's another line where they just line up, another line, another line. So they pile up, we say, one after the other. That will lead to the Hall patch equation of deformation of polycrystalline material as a function of grain size. So we see the first dislocation, it hits the wall and stops. And then the next dislocation hits the stress field of the first dislocation and stops. And the next one hit the stress, respectively strain fields of the previous dislocation, and then they cannot move anymore. They all pile up when moving towards the right hand side. So if I have another dislocation here and it moves, eventually it stops behind the other dislocation and cannot move further without overcoming a large energy barrier. People also do simulations, computer simulations. So here's, for example, a huge simulation of dislocation dynamics within 1 billion copper atoms, so Cu atoms, FCC lattice, which has been computed at the Lawrence Livermore lab in year 2000, so 22 years ago. Computers were not as powerful as now, but even for nowadays, this is a huge simulation. What we see there is the dislocation network. They show only atoms which have some meaningful displacement u, or this registry u, and all the other atoms, they are kept transparent. so that you can see, so that you can look into the dislocation structure. So what do they write here? On the LLB, Lawrence Livermore Lab, a new simulation has allowed for the first time the study of formation of complex junction structures in metals undergoing work hardening induced by tensile strain. This simulation was performed in the fall of 2000 on several thousand processors. So you need a lot of processors, computer processors, of the initial delivery ASCII wide supercomputer at the LL National Lab, Lawrence Livermore National Lab. This is the work of these people, Abraham and Almaden, research in collaboration with other personnel, Duchesneau and Diaz and Larubia. Oh, some famous people, yeah. So you need a few thousand processors to compute this kind of dislocation structures by simulation. But this is feasible nowadays, and you know, in 20 years the computers became much better. Here other simulations, indentation into the 100 surface of a copper single crystal. Indentation is you have a small point, and the point you push into the surface like a needle into the surface, and then you deform the underlying crystal, and you can measure hardness, but you also can measure a strain stress curve nowadays if you have spherical indenters. That's a very powerful microscopic strain stress testing machine, not just for hardness testing. So you really can get local strain stress curves out of it. Well advanced with computers and modeling. Then the details of the dislocation emission in a molecular dynamics simulation of a metal thin film under nano indentation. We know people at GTIT, there's a group doing molecular dynamics simulations. So we at GT, Professor Wang, he does studies, for example, in this direction. Another nice movie I found on dislocations is shown here. We have the situations of a screw edged and a mixed dislocation moving through a crystal. So you see the displacement, the Burgers vector here. Oops, the Burgers vector in this direction. And I touch it, it jumps. And now we play it again. And look to the screw dislocation. It moves perpendicular to the Burgers vector. Play it again. The edge dislocation moves along the Burgers vector, the direction of the Burgers vector. And then we have the mixed dislocation. So look to the mixed dislocation, where we have part screw, part edge. So the line moves diagonal, and which is a superposition of screw and edge. Let me check the time. Okay. One of the observation methods is transmission electron microscopy and diffraction. This takes more than 5 minutes for me to introduce, so I better stop here and resume there next time to finish up with the characterization of this dislocations, and then we come to effects in materials where the dislocations play a role, like slip planes, macroscopic slip planes, orientations, hole patch grain size dependence, and so on. Is there any question right now? Still there? Okay, maybe people are tired, want to go to dinner. Swan chat, good. 11:53, yeah, that's now, yeah. Okay, thank you. I will upload the movie soon, as usual, and catch you next time. Bye.